If you don't know Sierra or haven't requested a quote from Sierra, please do so. We're in the Bay Area in Silicon Valley, and we have about 100,000 square feet of manufacturing. And we really work as a partnership with our customers on complex designs, both PCB and assembly. And reach out to us if you have a need. So today, this will be the agenda. We're definitely talking about laminates and stack ups and some, right ways to do stack ups and why stack ups are important, and then really understanding a fabricator's capability as much as you can upfront. And then, of course, the main point of the webinar, the I would say, is the DFM and how to, understand DFM, and then, Valor will give a demo of that. Okay, so picking materials. Picking materials is definitely becoming a little bit more complex, and it really needs to be per what your design looks like. Um, so one of the key factors is, the material electrical properties, of course. So you want a decay less than 4, for faster signal propagation. You want to really take a look at, materials in this way if you have impedance requirements. And you also need to understand how the energy is flowing through the material, looking at the loss tangent of the material. So these are definitely important. Now, how your material performs versus the data sheet is different. So, getting input from the fabricator, in terms of the impedance modeling and uh, any kind of electrical performance is a key thing. If not everything performs to the data sheets. The other thing to look at is the CTE, or coefficient of thermal expansion. If you have design requirements like stacked laser drilled microvias, and you're picking materials that are not appropriate for that type of a design, then you're going to end up with uh, subpar, sub-reliable PCBs. And it's really because of the material you chose, is not working with the design that you have. So both these, the DK, DF, CTE, they go along with, what is your application, what is your design requirements, and not just isolated decisions. But a CTE is important in PCB manufacturing as well as on the assembly side. You want as few mismatches in CTE as possible. Okay, and the other one is TG, or glass transition temperature. We're getting lots of designs which have 3, 4, 5 lamination cycles. You have to be aware of the T sub G, because it can result in, all these kind of issues of cracked vias and, lifted pads, delamination, all these things can happen. So these are some guidelines for, choosing the right T sub G in your material as well. So, when you're looking for designing a stack up, and you have an idea of the HDI portion, you have an idea of the signal integrity that you want to achieve, you also have to create a mechanically good stack up, which basically means, you don't want to risk warping or risk any bending or flexing during the PCB process or even in the assembly process. There's a lot of boards that we're building right now that just require fixtures to hold the board, in place as coplanar as possible during the assembly process. Even if it's a thick board, it might be too heavy, or if it's a thin board, you know, an array is not enough to hold these boards in place during the assembly process. So understand your stack up and understand that there's no induced warpage in the stack up. And as we're building the product, if you have a core that has uneven copper distribution, like a 1 ounce and then a 2 ounce on the other side of the core, understand that that can impact overall yield. So knowing where the fabricator is going to be placing cores and or as a designer, knowing where the cores are is critical. And then, of course, the tighter the distance between layers, you're going to have a better, coupling, and that's good for electrical performance. So. For just overall strategies, really understand copper distribution on each layer. That always has to go into our DFM as well, like understanding what the layer is and understanding, do we have enough copper to really have good adhesion during lamination and good even etching. And of course, every design is unique, so that's where you get, the feedback from the fabricator comes in. I've talked many times in webinars about parallel lines and, interesting features like coils. Not every fabricator will flag those as something special to look at, but, that definitely, those features definitely are special. And you should put those into your notes as highlighting them as special. So understanding the topography of each layer, understanding, where you're putting your copper pores and whether that'll be able to etch well, that's all important when it goes into the strategy of stack-ups. So here's some, kind of key things that you must have on your fab drawing, in order for a fabricator to really be able to produce a quality product. You don't want to leave your fabricator hanging without proper notes. And if you copy and paste notes, which everyone does, you definitely want to go through those with a fine-tooth comb. Make sure that you're not, kind of sending your fabricator on a wild goose chase, going down a path of hey, what does this note really mean? And it's conflicting with, your actual data. And that happened because you just kind of didn't review your own notes before you sent them over. That will definitely delay the engineering portion of the build. And everyone wants things fast. So sending in, very, very well reviewed data and fabrication drawings prior, and not just throwing them on the wall, that will make things go faster. So I think one tool we have is our Stack-Up tool that really helps get people close to ready. And so Vandana is going to do a demo of that.
Yeah, so today we have a Stack-Up Designer tool that offers a categorized library of pre-designed stack-ups. As you can see, the low-cost stack-up, the standard, high power, high frequency, and HDI stack-up. We also have an option tailored for complex VGA designs, as you can see here. Let's select the standard stack-up for now, and then start entering the project name, the PCB size, type, the layer count. Uses drop-down to choose the material, choose a target thickness. Then you can select the inner rounds, the outer rounds, and then you have a few other parameters here, which already have default selections here, but you can change them if you wish to do so. And click on Generate Stack-Up. And you can see that a stack-up has been generated here based on what you have selected. Here you can change the signal plane layer. Let's just change this to mixed layer for now. And the copper percentage is automatically adjusted. And the diagram is also changed accordingly. Here, the traces and vias are positioned based on the stack-up and the layer sites with improved representation that allows direct identification of trace orientation and layer type, along with clearer via connections between the layers. Once you're satisfied with this stack-up, click on View Detailed Stack-Up, and you can see a detailed construction of the stack-up that you have designed. Then we have three other tabs here. The first one, the control impedance. You can just add an impedance model here. Click on this button, choose the model type, enter the impedance layer number, the first reference layer, the second reference layer, enter a target impedance, a trace separation, click on add, and then this impedance line will be added to the table here. You can add as many impedances you want to. Click on this edit button, and the whole of this impedance calculator will be displayed here. You can recalculate by modifying some of these parameters here. You can calculate your W's and impedances here. Then we also have the signal loss calculator. You can confirm these values or change them if you wish to do so. Click on calculate loss and you can see the signal loss output in the odd and even mode are calculated and displayed. I've also just shown the calculations for S parameter calculator, as you can see, and the crosstalk calculator as well. So let's move ahead to the next tab, that is the VIA information tab. Here, click on add VIA button and you can add a VIA here using the drop down. Change the drill diameter or the VIA pad diameter, click on add, and then this will be added to the table. And the VIA current capacity and the temperature rise are also calculated and displayed. You can click on this edit button and the tool will open and you can modify these values and recalculate. Then we have the trace information, wherein we have the trace with current capacity calculator and the PCB conductor spacing calculator. Let's just demo this trace current capacity for now. Choose this drop down to choose a parameter to calculate. Let's go with conductor width. Enter layer. Then you can enter maximum current capacity here and click on calculate and add. And you can see that it has been added to the table. Similarly, you can use a conductor spacing calculator, and then we have a few other options where you can print the preview, you can modify the stack up by going back. You can click on the save stack up button and save the stack up that you have done, so that you can come and click on this view saved stack up list, and then you can modify your stack up again. In the export option, we have a number of options here. We have the Allegro and Altium start file. We also have the Allegro Altium stack-up files, and you can download it in the IPC 2581 format as well. And you can directly import this into the ECAD tool. Then we have the Altium rule file and the instruction manual, which has instructions to import all these files into the ECAD tool. Just click on any of these buttons and you can download your file. Thank you so much.
All right, so I'm going to spend a little bit more time on stack-ups, and specifically hybrid stack-ups, and RF designs. So let's say you have an RF design and you're using HDI technologies like laser drill microvias and sequential laminations. The material itself has to be conducive to that type of manufacturing. So again, I mentioned in the beginning, you're picking materials for electrical properties. You're also picking materials for your end use application, and you're also picking materials you should be picking them with manufacturing guidelines in mind as well. So in a hybrid situation, it gives you more flexibility to have the sub-lamination structures, or let's say build-up structures, in traditional materials like FR4s or 370HR or Ventec or whatever material is the choice of that fabricator, and then have a hybrid or outer cores being the higher speed materials that don't process the same way or as easily as an FR4 material. So that's one, to me, a huge advantage for having hybrid stack-ups. Now, when you have hybrid stack-ups, there does come into play scaling, meaning one material like a Rogers will stretch and skew differently from an FR4. So the fabricator is going to probably have to run a first article as boards get more and more complex that are being made in the US, for RF, military, aero, those type of industries. There's really no clear scaling data that a fabricator has already built that job or something similar to reference. So I think most people are following the process of running a first article to get the scaling data and to dial in these parameters, for the different recipes of the different machines. So that's kind of, you could say, the downfall of a hybrid stack-up, but there's a lot of advantages to especially cost and things like that. So there's always plus and minuses. You can never really get everything. But so those are some things to consider, when choosing a hybrid stack-up. Like in this case, just one last point, I wouldn't want to see a full Rogers build here because of the things I mentioned. Rogers is a little bit harder to deal with overall, and so why have a full stack Rogers when you can have a hybrid? It'll save you cost and it'll be a little easier to manufacture for the fabricator. Okay, so now let's talk about a little bit of drilling. So drilling is important, of course, for many reasons. One of them is you don't want any, direct connect shorts, and you have to watch out for your drill to copper in that case. And a fabricator will typically increase your finished drill size on your drawing by 3 mils and plate down. So when you do your analysis of um, drill the copper, uh, try and see what it looks like after you've increased your drill sizes, a little bit, and then you kind of run your DRCs. You'll get a better understanding of whether you have any tight drill to coppers. But most fabricators, if you don't do that, most fabricators will run, the drill to copper checks once we receive the data from you. But the key thing here is that to understand that, you know, we are increasing the hole size, so you have to be aware of that. And, to make sure that you're following, again, the right uh, pad pad stacks for that material, for that class of product, class 2 versus class 3 is different, and for your fabricator. How well can your fabricator hold certain tolerances? So we're throwing in some guidelines about trace and space as well. And this is also true of drilling. If you're, drilling through more copper, you're going to have a little bit more drill wander. If you're etching through more copper, you have to be aware of the spacing guidelines so we can properly add etch comp. So all these things are a part of the DFM process, which are very specific to your design and what you choose. Um, Another slide on annular ring and how it really has to do with, class 2 versus class 3. And then, one way of a fabricator presents it is, okay, what's the drill size plus how much spacing do you need after that? And most designers think in terms of here is the maximum pad that I can have, and therefore this is the drill that I can do. And then that's also okay, but just get a confirmation from your fabricator that that the pad stack is good for the material, the construction and for their capabilities as well. If you have controlled impedance on your board, we have a lot of guidelines on controlled impedance, not just from how to specify that to your fabricator, but also how to minimize any impedance discontinuities with your design and your stack up, and how to route it the best way. So that's not this webinar, so there's plenty of guidelines for that. I recommend downloading our controlled impedance design guide or going back and revisiting some of um, the webinars we've done on this topic. Solder mask. Okay, solder mask and silkscreen. So for solder mask and silkscreen, really these processes are more for the assembly facility rather than the fabricator, yet the fabricator makes decisions on the on what is manufacturable. And so if you're not working with someone who does both fab and assembly, you're going to get partial feedback. And it really limits your ability to make an overall assessment and overall design decisions. Um, you know, so I highly encourage working with a fabricator and an assembler, and of course Sierra is both. But basically, I'll give you a quick off the slide example. there's something called peelable solder mask, which is a real pain for any fabricator to do. But if the assembly must or need a very clean area post assembly process, either you have to buy a fixture or you can use this process of peelable solder mask and keep that area very clean up until the end of your manufacturing process. So these are the type of decisions you can make and trade-offs you can make if you're a fabricator and an assembler. Other than that, when you're designing your PCB, be aware of the copper thickness because copper thickness absolutely plays a role in how you should design your solder mask webs and your solder mask openings. That's a key portion. Sometimes you can have chemistry entrapment and all these other things can happen, during the manufacturing process of solder mask. Something else off the slide is the color of solder mask does matter because so green versus red versus blue versus black, these all have different DFM guidelines. And so that's something that we've put into our DFM rules when we're checking your data, what's the color of the solder mask? And then therefore, what are the rules that we can have? What are the spacing that we can have for your design? Some general capability guidelines and tolerances. I think also important is understanding, are you designing your board properly with thermals? Are you managing your heat properly? What are you doing with your stack up to manage the heat properly? So all these things are important in your DFM to make sure that you can assemble it and the board functions properly in the field. And then we have some quick summary on the PCB DFA, what we call DFA for assembly. How close can you have components together? How close can you have components to the edge of the board? And of course, number one is always pin one markings and polarity. That always seems to be an issue for some reason. Look at the data sheet, clearly outline what is pin one. That will save your assembly shop a lot of effort. And then lastly, I'm going to give a shout out to fiducials. Fiducials are important as the boards are either getting more dense or if the boards are very large, board material moves around. So it's not what you see in the data is what you get physically. And so assembly shops need fiducials to align to their equipment. So fiducials are important, and if you can have a fiducial on your board next to a sensitive component, that's even better. Otherwise, we'll probably end up putting fiducials on railings for the array. Now that's it from my side.
You can see it. Okay, great. Okay, so again, my name is Owen Manor. I spent about 13 years with Siemens and Mentor Graphics before that. Heavily involved in the Valor product lines. I did lose my voice over the weekend. I've been doing a lot of work on trying to get it back. A lot of the honey and tea and ginger. I hope it stays well for the next 15 minutes or so. And going on. So, I mean, this is kind of right the flow that we have from design to manufacturing in PCB, right? We do the design, we then hopefully, before the handoff, we have a step there where we're doing some validation as well as design for manufacturing. And then this goes into process engineering, both for fab and for assembly. And then, of course, production and finally box build. And we're really going to focus today on, kind of the second half of the design and the DFM parts where DFM is actually kind of applicable, right? And we're really trying to answer two questions. In design, we're really trying to answer the question, can I design it better, right? I always want to create, right, have more functionality in the PCB. I want it to be more dense. So can I design it really better and meet all of my requirements, but still get to a reasonable yield and quality? And then when I'm done, can I really manufacture it, right? And these are kind of the questions that we're going to be talking throughout, this. And the main application that we're going to be focusing on is an application called Valor NPI, which has about 950 DFM checks. So really, DFM is really, we're trying to simulate the PCB fabrication and assembly process in design to the best of our capabilities, right? Because we want to find manufacturability issues in advance, because as we all know, that's going to save us time and money. So this is in essence what we're trying to do. Now, there's a lot of misconceptions here, in the market, and I'm going to go about, some of them. First of all is, my supplier can handle all the DFM for me. That is true. And Sierra has a lot of DFM capabilities, right? But as we'll see, next, it's not a replacement for you doing DFM. Having your supplier do DFM is essential and is a must, but in many cases, it's a little bit too late in the game, right? Because you've already finished the entire design. So you're still going to have to do rework. And if the design is complex, you know, that's not very
Mm-hmm.
efficient. And second of all, not always do your, as a designer, your objectives and interests do not fully align with the supplier. Okay, and we'll go into that. Um, Amit did mention the word DRC, and in Siemens, we really try to differentiate between DFM and DRC. It's not the same thing. DRC is a must, and you all need the DRC, right? Design rule checking. But as we go, it's not exactly the same thing as DFM. And there's a notion out there that, why can't we do DFM? Because it's just very difficult to set up. So we'll talk about why it's not that difficult, and really anybody with a little bit of focus and motivation can do that. Right, DFM is challenging. We'll talk a little bit about that. Um, it's good enough to run DFM at the end of the design flow. Well, it's definitely better than not doing anything, but also, as you'll see in the presentation, it's also a little bit too late in the game. And finally, DFM is only for large enterprises. That used to be the case. It's not anymore. So we'll really say, guys, that this isn't really true anymore. Okay. And we'll go one by one. So, regarding who should run DFM. So, the truth is that probably both sides should be running DFM, right? Um, Amit and Sierra, they need to optimize their manufacturing process, right? They need to know that they're doing the most efficient manufacturing process, both in fabrication and as assembly. And second of all, right, they want to protect their margins. If they get a design, and this could be an adventure, and then start manufacturing it, they get to a lot of yield and quality issues. You as their customers might come and say, well, the design was flawless. It's your manufacturing process that created this. So they want to make sure that they protect themselves. But as a design guy, you want to prevent manufacturing violations, right? You don't want them to call you. And Amit was saying, for example, right, pin one polarity issues, wrong shapes. You don't want to get the call from them, and you really want to eliminate these respins. So both sides of the equation should really be doing. Many people ask us, okay, what's the result of a DFM? And Jose will go into that in the application in a second. But in general, of course, there is a visual utility that you go through as the layout engineer, the guy running the DFM, and you can go one by one and see the results and deal with them. But also at the end of the day, you get an auto-generated, very comprehensive, shareable DFM report. You can take this DFM report and share it with some experts you have on the team. You can share it with consultants. You can save it. And now, if things start going on in the field, this is a bit of an insurance policy, because you can show, guys, we did a DFM analysis. Nothing here was flagged, which means it could be a bad component. There's a lot of other things that could have gone into this, but it's definitely not the manufacturability of the design that you guys created. So that is one of the outputs of this solution. These are some of the DFM checks that we have in the application. Okay, we're going to go into this, but I just wanted to throw it out there. This covers both fabrication and assembly. In the demo today, we'll focus a little bit more on fabrication, but there's also a lot of assembly checks there. And really, we're trying to validate that we don't have issues around spacing and some of the stuff. And I'll go into the details in a couple more slides for you to understand, but it really goes along with a lot of the things that Amit was speaking about, such as, the drill to copper spacing. It goes into component to component spacing and stuff like that. We have specific tests around flex and flex rigid. So if you are in the business of doing that, there's a specific set of checks that were added in the last couple of years to do that. And also if you're doing any micro vias, HDI, then that's also included in the application. So, and this is really not DRC. So why is it not DRC? Because DRC really does not go into the manufacturing process. DFM looks at the manufacturing process. DRC will, first of all, give you kind of right violations. DFM also goes into this yellow zone, which means you're pretty close to the threshold. Academically speaking, you're fine. But from our experience, this will give us a yield issue, meaning maybe reliability in the field, maybe defects on the production. So cost. Now, if you don't have a choice and you need to do this, then you can definitely do that. But you should take into account that this will have a business impact. So here's an example. If you're doing an annular ring, DRC uses a minimum annular ring, right? DFM will do that based on the manufacturing process. Is it a laser drilled, like Amit was talking about? Is it a laser drilled via? Is it mechanically drilled through hole? Is it a back drilled? Because each of these processes have completely different constraints. And as Amit was talking, drill to copper spacing. So DRC has one, but here we're going to look at DFM at the manufacturing process. Is it going to be plated, non-plated? So we are looking at the manufacturing process. And that's why it's very different than how DRC. So DRC is definitely a must in order to have, the same level of quality design throughout the team and throughout layout and make sure that best practices are kept. But DFM is definitely a complementary solution for DRC. And another thing that we're slightly going to talk about, but not too much, is the VPL. So VPL stands for the Valor Parts Library. It's a library created by Valor about 20 years ago and has about 250 billion manufacturable part numbers and their accurate geometry. So we have downloaded the datasheet for you. We have looked at the datasheet and we have captured all of the geometric properties, the component size, the height, the shape, the pin location, pin width, and all of that, and the pin 1 location. So if we have an MPN, okay, so we need something that you can stick in DigiKey and find that, okay, no internal part numbers or customer part numbers. And then based on that, we can take that package and do a solder paste analysis and also a component spacing and a pin to pad. And this is how we catch a lot of those polarity issues and a lot of those rotation issues because we can do that check. So that is something that we definitely recommend to do and will help finding some of those issues that Amit was talking about. We're also using AI these days in order to generate that. So, improve that information. And then we can do some of these kind of, solder validation here that we can do and so on. What you see on the right, and if you've been in the industry for a while and of doing DFM, then this used to be called an ERF file, engineering rule file, which was invented 25 years ago, and is a text file with thousands of lines of the different measurements that you're going to be checking. This was adequate maybe 25 years ago, but today it's not acceptable, right? No Gen Z out of college coming into work with us who has an iPhone and an iPad is going to be doing that. And honestly, it's very hard to manage it. And if you're not living in the ERF file and updating it every couple of days, you forget it, you can't find it. And then what happens is that over time, nobody updates it. The guy retires, and then you're essentially checking for a manufacturing process that isn't even relevant anymore. And you're getting a lot of false calls, and the whole DFM loses value. So we've completely changed how we actually now manage it. So we have something called design factors. So we use those to automatically assign the DFM constraints. So we don't need to manage now tens of ERF files because this is used dynamically, and Jose will show it that, for example, based on copper weight or based on number of layers, we can define the DFM thresholds. The other thing is design classification. So we can automatically see stuff on the board like microvias, and then we can actually, apply the microvia solutions. And finally, manufacturing constraints, so we can bring those in as well. And we have this new graphical user interface for doing these things. It's called an analysis definition manager, which makes the whole DFM implementation and usage much, much, much easier. Okay, let's speed up a little bit. One more thing that we wanted to go into is leveraging PCB flow. So PCB flow is an ecosystem that we've created to share manufacturing profiles between suppliers and designers. It's very easy to use. It is free as an ecosystem. And one of the big advantages with it is that IPC has decided to join us here, and they have published some DFM profiles on the PCB flow ecosystem. So anybody using Valor NPI for doing DFM, whether it's in Altium, Expedition, or Cadence, can download those Siemens PCB flow, these IPC profiles from PCBflow.com and use them. So if you don't want to go into the effort of creating your own DFM profile and you want initially to do something, this is a good starting point to do that and get some immediate results. This is a little bit about what I talked about, the microvia example, and I think you get that, and it's all good. So before we go to, Jose, some of the customers we talk to, right, they do the DFM really when the board is complete. But that means it's, of course, better than having it, found on production or in the field. But this means that you're still doing these internal engineering ECOs, and this is like a revision spin, right? So it's really not very efficient. In every stage of the design flow, we have some applicable checks that we can run. We can run some in library cell review. We can run some during component placement. We can run some during routing of the PCB and so forth. So you don't have to run the whole 950 checks at every stage of the layout. You can choose 20, 15, 10 checks to run in these stages as part of your design review and the validation done before going to the next stage. And you can find those issues very early on in the design process when it's very easy to fix and very easy to do something about. The only thing maybe I'll add is the AVL stuff. We did talk a little bit about that. Many of you do an initial design using some internal part number, but once we go into production, we use alternates, right? Everybody uses alternates. And in many cases, the tolerance between these components is slightly different. So what we can do in the DFM application is actually do an analysis of all three components and make sure that they're all good for that specific design. And it could be that B and C are good options, but A has a significant issue, and then we have to tell procurement that we need a different component. Okay, with that, I think I'd like to move it to Jose. Jose, do you want to share your screen?
What we're looking at right now is the Valor application, Valor MPI application. This particular screen is called the MRA, stands for Manufacturing Risk Assessment, and this is basically where I do run all my analysis and get my results in this screen, this GUI. There's also the Analysis Definition Manager that Owen mentioned a minute ago for configuring and setting up all my DFM profiles for the rules, values, and all the stages. It's all the setup. I do it in an Analysis Definition Manager. I'll start with showing on the right side of the screen, we have the results. So I did actually run this, the analysis on this design for fabrication and assembly, basically a complete analysis. The results are divided in categories depending, actually based on the way that the rules, the setup are, and the setup rules are. So the analysis rules are, and then these are the main categories: edge, solder, mechanical, component placement, quality, process, setup, and net list. And this summary is showing us the level of the amount of results that I got in each one of the categories. 47 out of my 100%, 47.6% is edge, fabrication related, and 40 solder. And the rest of them are having, less, a smaller number. So If we start with the edge, if we click here or here on the tab, is the same. We'll see these are not the total number of results. These are the results that I decided when I went through the reviewing the results. I decided to report it. Whenever I see this green check marks, it means that I reported. I selected this result to be reported, and then it's going to be included at the end in my final report. If I turn off my filter, you can see that right now I'm showing the reported. Now I'm not showing the reported only, and I'm showing the entire list of results. So I have different results in different categories. It starts with signal layer here, and then subcategories like the catchwords, stops, slivers, white trace narrow. So I went through my list and I decided which ones I wanted to report. Those are here, the ones with the check mark. So I want to show you this since it's going to be what is going to be in my end report, but in my final report, but I just wanted to show you the entire list for a second. So I have this check, for a chord that is going to be reported. I have stops, I have slivers here, the potential acid traps, this white trace narrow, and sometimes it's like, well, I'm going through the list and what is this check, looking for? And it's very difficult because we have almost 1,000 checks available. So, but I have this little button here for showing the description. This is very handy because it's showing me the description of what is this specific result came from, which the check that is what it's trying to find. And this one is preventing like this white trace narrow is preventing an imbalance of copper that could lead to solder starvation, for example. So it's very handy to have this. This is slivers for acid traps. I have if you notice, I have slivers here and then I have slivers here. It's the difference is very interesting because with Valor we can also assign DFM areas, and that's very handy. If we have this layer like the Fab DRC layer, for example, indicating or defining the specific DFX areas, if I go here and I select this guy here, you'll see that in the information, the DFX area name for this specific area is CPU. So this, if you notice, this result has CPU as a suffix, as a prefix, then it means that this sliver is in the CPU area and only. And then it's gonna be other result indicating, an sliver in a different place. But if I go back here, you'll see that this is in the CPU area. If I turn on the Fab DRC again, so this is a very nice capability because I can actually not only show the results that way, indicating that they belong to that area, but I can actually set a different value for the same check that it only will be affecting this area, which is the main purpose of having these areas, because you can have some specific checks that are needing to have different values for the check on that specific area, on those specific areas, than the other areas, right? So that's totally capable of doing in the ADM and Analysis Definition Manager setup in Valor. And if I go to another area, you can see there's another name. I think this one is master. So you'll see master in my results as well. So whichever areas I have, this is DSBA BGA breakout. So those can be having different values for specific checks, and I can apply specific checks only to those areas and nowhere else. So very, very, very important functionality that I have there. Very useful. So if I keep going, these are just few examples. This is path to circuit. This is component. This is copper spacing, of course. And you can see in my results, there's always most of the results I have this red, yellow, and green. This indicates where it fell in my ranges or values. the way that the value checks work, the majority of them, they work with these ranges. So these are the values. 4 is the yellow, is the nominal, 4 mils. Then 3.4 is basically red, and 4.6 is yellow, is green. So everything between 3.4 and 4.6 is going to be yellow, falls into the nominal. It's a warning, it's at the nominal level, but I mean, it's not like I should forget about it, but I should keep it in mind because it's basically on the limits. But the highest level offender, it's anything that goes 3.4 or below, it's going to become red. So what I said in the definition and the setups in the setup of the constraints, I set the nominal value, the yellow, and then I set a tolerance. Normally by default is plus minus 15%, but I can actually adjust the tolerance, or I can set a specific values for the red, yellow, and green if necessary. So it has all the flexibility on that matter, but I just wanted to explain that for you to have the overview. Then basically, I have this. I mean, I have the annular rings, of course, a measurement, and I have, all the paths analysis, the path stack analysis, things like that. This best practice, that is checked as well. The direct connections in between paths, that is not a part of the best practices, for VGAs as well. Holes present on SMD pads, for example, in this case, it was for an SO. It goes actually by package type. In this case, for this check, you see SO, then SMT miscellaneous for chip, so all that kind of situation, all those situations will be reported. This is very interesting one as well. This one is reporting the trace width ratio violation, which means that we have copper imbalance. This is an 0402, so it could be, leading to the component being pulled to the side where we have more copper, of course, in the worst cases, it could create a tombstone effect. So we need to, of course, for those small components, or in the smaller 0201s, for example, this is a very important check to, look at the results at. And we also have a check for making sure that the pad sizes are actually suitable for the components. And in this case, it looks like because of the component type or the component that is actually assigned to this place, it's not going to be fitting correctly. And that's also, this is just the edge, check by checking the pads, but there's an extended, list of checks for the component assembly as well, checking for the solder joints, checking for the spacing, pin to pad, all that. But this is just, the edge, the fabrication. It will detect this kind of issue even if we don't run the assembly analysis. That's the advantage. We also have this annular ring situation and the signal layer checks and the V annular ring. I wanted to show this because sometimes we get like this rule says, 6 is the nominal value, 5.1 is the minimum. But then if I turn off my filter here, I will see that this category has actually a lot of results. Where is my annular ring? This one here. It has a lot of results, and it has 338. And this one is a little different one. This one is the one I was showing. This has 5,000 results here. This is the indicator. And I don't want 5,000 results. What I can tell very quickly, and this is another advantage of having this histogram section. The histogram is actually meant to be used in these cases where my rule says, 5.1 is the minimum, 6 is the nominal. But if you notice, by looking to the histogram, it's pretty obvious that most of the analysis results are on the 4 mils. So meaning that my board design, basically all the annular rings are in the 4 mils measurement. So my rule will need to be adjusted, and that's when it's actually very practical the way that we can adjust the rules. Of course, I need to be an administrator, So I need to log in as an administrator. Not every user can do this because this needs to be controlled, only restricted for administrators only. But when I have this type of situation, I go and click on this button here that opens the analysis definition manager. And the analysis definition manager is showing me the specific rule and the values that are actually giving me those results. In this case, if you notice, I have the red, yellow, and green here, the values. And remember that my value was 6, but I have multiple rows here. And this is because of the way that the ADM works, which is very, very good, because I have different classifications. The classifications are, in this case, I have 4 classifications driven by different factors. So this is the way that the system recognizes what type of designs I'm dealing with. And then in my preset setup, is going to be applying, the rule set that applies to that specific design type. If I run a test here, I can tell that it did run complex, because based on the conditions that are preset for the the different technology levels that I did set here, standard, advanced, complex, micro, based on the factors of the typical trace to trace and the typical trace width, the one that this design falls into this classification of complex and micro. So it's going to be applying complex actually, because it's the highest level. So the values that are going to be applied or are being applied at the ones that I got this results from are the ones that are under complex. And if you notice that we have top, bottom, inner, so it's inner and outer for complex. So these are the values that I will need to adjust, so my results can be, not flagging this biannular ring anymore because of the 4 mils. I will need to adjust it to, to be the nominal maybe 4, right? So that won't be, giving me the that false result anymore. And that's, part of the fine tune of the rules that is very, very friendly, very user friendly for on Valor MPI right now. Then let's say, okay, well, this is just, for this result, but you know what? I need my copper spacing to be driven also not only by the layer position of the drill side that is the default here, but I need it to be also driven by the copper weight, the copper thickness. So that's possible by adding the copper thickness factor here. So I have this factor button here, factor constraints factors tab. I can add, those are the factors that are already there, like my layer position, assembly process areas. But I can add from a preloaded the board thickness, or the impedance, or the copper thickness here. If I want to add the copper thickness, I can add it here. I can add my valid values that I utilize. Let's say it's 0.5, 1, and 2. These are my values. And then if I go back to my constraints in the general copper spacing, I can now turn on the copper thickness, factor here. And automatically, it's going to add another column with all the combinations by classification, layer position, and copper thickness. So now I have the liberty of setting specific values, not only by layer position, by classification and layer position, but also by copper thickness. So without needing to go back and forward in between checklists and changing rule sets, or as we call them in ADM, DFM profiles. In the same DFM profiles, I can cover all the combinations, all the possibilities. So when I before the application runs when you're prompting to run the analysis, it's going to scan the board looking for which classification it falls into, and then it's going to scan the stack up looking for the copper thickness as well. So depending on the classification and copper thickness is which constraints values are going to be applied automatically, so that I don't need to worry about that. And it also looks for the type of technology, if it's rigid flex, micro via, or HDI. If it falls also into that condition, if it complies with that condition, one of those or all of them, it will run also the checks that are related to HDI or microvia. We have a bunch of microvia checks that are, of course, everything that is enabled with the values that you set in your profile, or flex, right? So it's it's really, really convenient the way that the setup is. And we also can, you can think, okay, well, I have a lot of checks enabled in my setup, in my profile. I have probably an amount that I don't want to run every single time. I want to have checklists for what we call stages. The stages that Oren mentioned earlier as well. This is the way where I can actually select a subset selection of the list of constraints that I have here, the list of checks, and then run them individually. So, for example, I have production ready, and if I go through the main list, it will show basically that everything is included in this production ready, a stage. But let's say I want to run just a few checks. So if I go to Jose Special that I just created, it will show me that I have just just a few constraints, selected for running that. And I have some other, preloaded stages like solder validation or basic fabrication. There's a number of preloaded stages, but of course I can create my own, and then and then assign any analysis checks that I want. Let's say I just want to add for this specific stage, I just want to add the same net copper spacing, and it's only one check because I'm doing some testing. Maybe I can go through and I don't know, I want to add another check here, the biannular ring, and that's it, right? And I can run it. I can just save it, and then save my setup here, and then go to my analysis run. I select my new stage, and then I run the analysis here. Of course, I have too many profiles here, but this master sample VPL is the one that I did run for this. And you can tell here in the results, it tells you master sample VPL complex, which means the classification. That's the profile and the classification. If I go back to the results, it's master sample VPL, and then here you see the classifications. It did run complex, and I can tell on the constraints, the complex there, and I have all the flexibility and the availability of running everything the way I need it, configuring the way I need it. Of course, I can have more. As you can see, I have a bunch of DFM profiles, so I can create a copy of this. I have +1, +2, or I can create my own from scratch, and then I can set it specifically, and I can go back and forth and run multiple profiles, not only one, and then go back to my results and see different results. Like here, I have 2 different results from different profiles. So I can actually turn on and off, the results, so I can see only the results from one profile or both at the same time. So if I go, here, this is just one profile. If I go here, I have 2 profiles, and then I can, go back and forth and combine results if I want to. And all of them will go into my report as well. So if I'm happy with my results right now, then I can, generate my report. I go just results, generate report, and I have an option for Excel. This is Excel format, HTML or XML. If I want the raw data, I can do that. Normally, I go with Excel. It's a bit more convenient. Then I get a report like this. And this is very easy to generate, very easy to share. And it brings the general information, like the fabrication technology information, component information for the amount of components, pin count, BOM information, unique CPNs. Even if we're using valor parts library, the coverage of the valor parts library, so the heat rate. And then the results are going to be here, like MRA. Remember the edge solder mechanical. So if I click here, everything that I added the check mark or highlighted to be reported is going to be reported here. Remember this guy here. So if I click on the picture, it's going to give me the picture and also a screenshot of the location on the board map. Of course, the result gives me the XY location, which the title of the check, the range, the values there, the severity, the features or components or any elements that are related to that specific result. In this case, is some features and nets. But if it was a component that is related, it's going to be giving me the part number, manufactured part number. If I did load the BOM and everything, so I have all the results here. I can go back and jump in between categories. If I want to see the solder results, is the same format here, different results. So I have this results for the solder validation here. It's telling me, if I have an issue with the that heel and toe, the annular rings, slivers, the solder mask, pad to pad, all that. So this is, the general report, and it also has this very nice section for components, which is very well appreciated by the manufacturing areas, where it gives me the summary of components, all the placement lists, basically rep this, side, part number, package, X, Y, angle, rotation, even the component height is here. BPL packages when I use Battle Parts Library, manufacturer part number. This is very, very useful on the manufacturing areas. Manufacturing areas always love to have this component placement list. I think I am.
Yeah, I think you're good in time. Do we want to take some questions?
I think in the end, when it comes to design, let's back up a little bit. The first thing you need to do when you're starting a design is you need to work with your supplier from the very beginning. Even before, this is part of that shift left that we've been discussing now for a little over an hour, of taking that manufacturing and starting from the beginning at the point of design. This is where you get that manufacturing driven design. So from a design engineer, when you're starting your design, whether it's starting with the stack up or at the definition of your design, you have to have your supplier as part of your external stakeholder at the table. So that way, when you have your rules or what you're checking for, your DFM, your parameters, you have that input at the point of design. And this is where it's designed correct by construction. So when you're doing these checks are just verifying that your design is correct and you have the least potential for any issues that may present themselves downstream. And so when you look at this, like for the V scoring, that first question, does adding a frame change the board? These are the kind of questions that you would get answered or get addressed up front in the beginning if you're going to create the panel yourself, or you're going to give the board one up to the supplier and let them figure out what is going to be the best mitigation to handle that. And then I think the second one is, are the assembly markings meant to be large enough to read on the print? I mean, let's be real. Nowadays, every design engineer, when he gets down in the lab with the board, he has a laptop right there and he has a PDF on his laptop so he could search. So the print, I don't want to say it's kind of irrelevant, because you could zoom in all you need to. Whatever is best for your guideline within your company, I would use that, and whatever works for you. I mean, I don't think the print needs to be very large, because you have a PDF and you could zoom in digitally now. It's not like years in the past, like early in my career, where everything was photo plotted and you had these big plotters that had to plot out a PDF or a drawing. Nowadays, in the digital age, it could be very small because you could just zoom in. So I don't think that is an issue anymore. The next question: can you provide suggestions for specifying material when you don't know the material, what your dielectric and copper thicknesses are? I think in the beginning, when you're starting your design, working with your supplier to lock in the stack up to what you're up against, you need to know, and if you don't know, this is why you get on the phone and call your supplier, and you call Sierra Circuits and you ask them, hey, I have a design that this is what my target widget's going to work at, whether it's automotive, mil-aero, whatever the case, commercial, and you give them your requirements, what you're trying to hit, and allow them to help set you up for success on which material to use. Maybe you need a polyimide, maybe you need Roger material, maybe you need it, whatever FR4 or whatever the case, Isola, whatever, high speed RF, the supplier will help guide you to make the correct selection. So that way you're not guessing in your parameters. And whether you specify an IPC 4101 slash sheet or not, I mean, you have to be specific in the material you're asking for, Because if not, if you just give a blind 4101/126, there's a lot of material that can go within that specific slash sheet. So you need to be specific on what you're after if you're designing high speed, high RF content. So I think, collaboration with your supplier is key, especially when you talk about your fabrication document, which Amit covered about the accuracy and the correctness that it has to be. And not just reviewing that document with your internal team, but you have to review this with your supplier. So that way you're wording correctly and you state it appropriately according to the IPC standards, because IPC is the universal language. And in the end, that fabrication document is actually a legal document, because that is what the supplier is going to build to. And so you need to make sure you're correct and you're conveying your engineering intent to manufacturing. But it's a team thing. It can't be just you tossing over the wall, because I guarantee you, if you design something with no collaboration with the supplier and you throw it over the fence, your likelihood of getting technical queries or basically work stoppages and potential respins is significantly increased. So that should cover that second question there about the material and the slash sheets. And then discussing placement of thermal via and grounding slugs, I think that is something that you need to work with the supplier to understand their capability if they're using, the slugs, and if that's within their wheelhouse, and then how would you implement that in your design? That is something that it's going to be working closely with the fabricator to make sure you implement that correctly in your design. I think when it comes to hybrid stack-ups, are there any limitations regarding material combinations? I mean, CTE mismatch, Amit talked about that, not just within the stack-up in the Z-axis, but also of how you're distributing your copper, within the same layer in the XY axis. You have to make sure your stack-up is balanced, and understanding your CTE of the different materials of what you're using is key. And this is, again, I'll reiterate, when you're choosing the material and you're choosing whether it's two different or three different pieces of material you're using, you have to work closely with your supplier to make sure that it's actually fabricatable in the real world. Because we all know we could design anything on a computer, but when you get into the real world, it's a whole nother ballgame. And the worst thing to do is to spend 6 weeks or 6 months on a design, and when you pull the trigger, the fabricator says it's impossible for me to build that you just wasted so much time, and potentially that could be catastrophic.